happens in math, but especially so in this unit. So we're going to talk about sequences and series and what those are today. Okay? So essentially this whole unit is about patterns, studying patterns. So what I'd like you to do is I'd like you, before we do anything else, to see if you can complete the blanks for these patterns below. So good old, let's see if you can find the pattern and then finish it off. The very first one, what's going on here? How do we get to the next number? You minus 3. We're going to minus 3. Okay, so negative 8 minus 3. Negative 11. Negative 14. Negative 17. Good. So here, we're subtracting a number each time to get to the next term. And so what we call this pattern is this pattern has a name. And this name for this pattern, this type of pattern, is called arithmetic. It's arithmetic sequence. So there's a whole bunch of terminology I just threw at you. And we're going to talk about them. Okay? How do we know something is an arithmetic sequence? Well, first off, let's talk about what a sequence is. Okay? I'm going to zoom out for a second. It's very top there. If you read the sentence, I'm not sure if you did or not, it says, how do we know what a sequence is? A sequence are numbers that are separated by commas. Fourth block, I'm sorry. I'm always like by fourth block, can't speak anymore. Numbers are separated, oh, you can't see that. There you go. By commas. And they usually follow a particular pattern. So we know something is a sequence if it's separated by commas. So all of these here are sequences because each term is separated by a comma. And you might be asking, well, what else would it be separated by? Well, we can actually separate them with plus signs or minus signs. We want to add the terms together or subtract the terms. And that would be called a series, which is another part of this unit. So there's sequences and there's series. These are all sequences because they all are separated by commas, each term. We call them all terms, right? So this negative 2 is what we would call term 1. The negative 5 is what we would call term 2. Yeah. Term 2. The next one we would call term 3. Yeah, it's very logical. Makes sense, right? So so term 1 is the abbreviation. T1 is the abbreviation for term 1. Okay? And then it says here that a sequence can may stop at a number, it may continue. And I'm going to talk about that a little bit more later. So let's go on to the next pattern. So all of these are sequences. 1, 3, 9, and 27. What are we doing each time to get the next? Multiplying by 3. Okay? So that's, so the next 27 times 3 is 81. Yeah? 81 times 3, 243. And then 7, 29. Good. So this has a special name too. This type of sequence is called geometric. Okay. So arithmetic sequence, what did we do each time? In an arithmetic sequence, we're going to add or subtract to get the next term. So we're adding or subtracting by something called a common difference, in this case negative 3, to get the next term. Geometric, what are we doing each time? We're multiplying. So it's where we multiply by something to get the next term. That's geometric. The next one, what are we doing each time? Subtract by 3. So negative 1 you should have had, and negative 7. So meaning, is this arithmetic or geometric? Arithmetic. Arithmetic, right? Never heard that. Arithmetic. It's like you're adding and subtracting in elementary. That's arithmetic. Okay, next guy. What's the next one? I gave you a hint, and I really regret it, because I think you could have got it without the hint. 1, 4, 9, 16. So the next one is 5 squared, 25. So this was 1 squared, 2 squared, 3 squared, 4 squared. So what's after 5 squared? 36 and 49. Is this arithmetic or geometric? Or neither? Neither. Why is it neither? Are we multiplying by the same thing each time? No, like if you think of it this way, to go from 1 to 4, I would multiply by 4. Is 4 times 4 9? No. So it's neither. And we're not adding. To go from 1 to 4 would be adding 3, but then it's adding 5. And then it's adding 7. That's not the same thing every time. Right. Exactly. So that is the pattern to it, but is it arithmetic? No. Because it has to be adding or subtracting the same thing every time. All right, last one. Have you heard of Fibonacci? No? Some of you, yes? It's like the golden ratio, and it's a really cool pattern that's seen in nature. Did anyone figure out the next term? Matt? 13. So how did we get 13? So you add the previous two together. So 1 and 1 is how you get the 2. And then 1 and 2 is how you get 3. So you just add the 2 terms prior. So that means our next term would be 8 plus 13, or 21. And the last one, 34. 13 plus 21. Does that make sense? It's a cool pattern, actually. So that, again, is neither. Neither geometric. It's a pattern, but it's not a geometric pattern, or it's not, nor is it a arithmetic pattern.
So these aren't given any other name?
The last one's called Fibonacci sequence. That's the pattern, but they don't. Yeah, we don't have a special name for them. No, they just have a pattern. You could say that the D is the squares of natural numbers, right? They have characteristics, but they don't have a special name. All of these sequences are what we call a finite sequence. So much terminology. Okay, so there's something called a finite sequence and an infinite sequence. They are opposites of each other, I guess. Either it's finite or it's infinite. Okay, let's talk about infinite. What does infinite mean? Endless. Goes on forever, right? So how do we know if a sequence goes on forever or is endless? We finish it, it ends with dot, dot, dot. That's an example of an infinite sequence. It ends with dot, dot, dot. Finite, if something is finite, finito, finish, these are all like from the same root. If it finishes, or if it's finite, it has an end. So it ends with a period, or it just ends. Okay? Those are the ones that top one's finite, bottom is infinite. Okay? Pretty simple? Alrighty. Sequences can be described by a general mathematic expression. Don't you love math teacher lingo? Okay, so what am I saying when I say a sequence can be described by general mathematical expression called a general term? It's very like mathy. All we're saying is that many sequences, and the ones we study, we can make them into an equation. We can simplify them. That's really what we're saying. We're saying, yeah, we can make an equation out of them. If I want to predict the 100th term, I could do one of two things. One, I could write out all 100 terms. I don't have the time on my hands to do that. You don't have the time on your hands to do that. And that's what math is all about. Is there a faster, better way? Yeah, there is. If there's a pattern, we can actually make an equation so that we can find the 100th term lickety-split. Yes. Okay, so we're going to talk about how do we make the general term or the equation, the formula. So first thing, at T1, we talked about this, stands for which term? The first. So T1 is 4, T2, 8, 3, 12, 4. I want you to figure out the 8th term. Okay, so what you could do is keep writing them out. What are we doing each time? Adding 4. So then 20, 24, 28, and 32. There's our answer. 1, 2, 4. Term 4 is 8. Term 5 is 16. Figure out the 8th term. 128. So what are we doing each time? Doubling, timesing by 2. So you get 32 and 64 and then 128. Okay, so the first sequence, is it arithmetic or geometric? The first one. Arithmetic. Okay, so arithmetic because, why is it arithmetic? We're adding 4 each time. The second one is geometric. Don't turn the page just yet. I want you to add a little note. Okay? If they're asking for the general term, they're looking for T of n, the actual formula. Okay, T of n. Yeah, let's go on to the next page now. Okay, so we're going to focus on arithmetic sequences for the next couple days. Sequences and series. We already talked about this, right? We're adding or subtracting something, and whatever we're adding and subtracting, we call that the common difference. So that's our letter D, okay? Oh, that's not it. That's D. Okay? D is the constant difference or common difference. Let's call it common difference because that's what I'll probably call it as. Same thing as constant difference. It's what we add or subtract each time. So what I would like you to do down below, before we can actually get into making the formula, I want you to write the term 1 and the common difference for each one of these sequences above. And you can fill it in those spaces. T1 equals D equals. So D stands for the common difference. What are you adding or subtracting each time to get to the next term? Where you have to be careful is if you're subtracting something, you need to put that negative in for your common difference. So the first one, first term is 3, common difference, we are adding 2. Second one, first term is 100, common difference, negative 3. Because we're subtracting 3 each time, we're going down by 3, we want to include that negative, okay? Because we're actually decreasing by 3, not increasing by 3. The next one, what are we are increasing by each time? 120. We're adding 120. Yeah, good. So why did we do that activity? You're going to see that we need to pick out the common difference and the first term in order to make the general term, the formula. I know it's a weird name for formula, general term, but that's what it means. Arithmetic sequence can be represented in 4 ways. One of them is a graph. Now back in grade 10, you learned about discrete and continuous data. Which one's continuous, the first or the second?
Second.
The first. Okay, continuous is the first. The second is discrete. So, continuous means you can draw it without lifting your pencil. In physics, it's often things like time and distance, right? You can have fractions or decimals of the values. Time is continuous. It doesn't just happen at 0 seconds, and 1, and 2, right? There's time in between that. Discrete data is when you can't connect the dots. So an example of discrete data would be the number of people in our class on a given day. Why can't you have half or a decimal of a person? Let's not debate. Let's just say yes or no. No. Okay, you can't have half of a person. Or the number of tickets sold. Sequences is also, do you think it's continuous or discrete? Think about it. In between each term, do we want to look at the numbers in between each term? Not really, right? We're just looking at the pattern of those specific numbers. And so when we graph a sequence is always going to be discrete when we graph it. It's discrete data. We're just, term 1 is 2. Is there going to be half of a term? No, it doesn't make sense. So our x values are actually the n, or the term number. So we only have the first term, the second term. Can you have a 0th term? No. Doesn't even, no. Silly people. Okay, and this is the actual, we'll try to do that. This is the actual term, right? The actual, like not the term number, but the actual value of the term. The actual number in the sequence. So when we plot this, when I want to plot that guy, 2, what term number is he? 1. So term number 1 value is 2. So the first term, because if this is n, 1, 2, 3, 4, and this is t of n. Make it into, oh, you can't even see that. There you go. Let's move this circle here, get him out of the way. So here's my term, right? You can make it into like a chart. Here's n and t of n, and so far. So when n is 1, the value is 2. When n is 2, the value is 4. Third term is 6. Fourth term, 8. Now, is this finite or infinite? Infinite. So we can go ahead and plot the 5th term because it shows up. Uh-oh. Uh-oh. Really, I can't plot. There we go. Better. So that's how we plot that as a graph. You would not connect the dots. I know you're tempted to. Whenever you see dots, it's like so much fun to connect them. Don't. Okay? There's things we can print off online if you want. But, you know, this guy we gotta leave. I'm sorry. Gotta, like, resist the urge. We could represent it with words. So we're starting at 2 and then we're adding 2 each time. just to mention recursive, a recursive formula is not very useful. And this is why we actually, you're not going to be tested on it. You most likely won't see it. But if it does show up in your textbook, you need to know, just recognize it. A recursive formula is when you need to know the previous term. So what this is saying here is that the term I'm looking for is equal to the previous term plus the common difference. So for example, the 100th term would be the 99th term plus the common difference. Would you agree with that? Yeah. But in order to figure out the 100th term, you need to know the 99. So then you're still at the point where you're making all the numbers. And that's not making it easier for us. So recursive formulas aren't great because you have to know your first term in order to figure out each one. So the third term is the second plus 2. 4 plus 2 is 6. It's not very useful. But that's what we call a recursive term. So how do we make the formula? Well, looking at this here where I compared your n and your t of n, if you compare them, what's the relationship between the term number and the actual value of the term? Do you see that? If we're looking right here, guys, look at your n and your t of n. So here's one box. What's the relationship each time? It's double it. It's double times 2. So you could say, even though this is arithmetic and we're adding to each time, we could also say that your value of your term, t of n, is equal to 2 times the term number. So for example, what would be the 100th term then? 200. 2 times 100. Now that is much simpler. Yes. So we're going to focus on making the formula now, the general term. So formula, general term, same thing. Okay? So the variables that you see, I'm going to turn the page. You ready to turn, or look at the next one? Oh, maybe you can write this at the top. I forgot to mention. When something is a straight line, what do we call that? It was like the name of 3 of your units in Math 10. Linear! Yeah, so arithmetic sequences are linear. Arithmetic. Sorry, I lied about turning the page. You can write it on the next page too if you want. Are linear. Because they have a constant rate of change. They're going up by 2 every time. Okay, now I'm done, I swear. Now we can turn. Alright. So this is the formula that we're going to talk about and how we get it. T of n is any term. Usually, T of n is our last term. And I say it's our last term or any term because usually the term you're looking for is the last term you need. If that makes sense, right? Or if they give you a specific term, that's your last one. That's the last one they give you, then you're going to use that as your last term. So often we use T of n as our last term. T of 1 is our first term. D is the common difference. And then n is the number of terms. Okay, so those are what they stand for in the formula. And let's see how the formula is made. So if we look at this, would you agree that T1 is the first term? Yes. What's happening here? The common difference. Yeah. So the second term is the first term plus 1 common difference. Okay? The third term, so this is the first term, n equals 2, n equals 3. So the third term is the first term plus 2 common differences. Yes? Or you can think of it as the second term plus 1 more common difference. And so if I add a common difference to this, it becomes 2d. If I'm adding another d to this. Okay? The fourth term is you're adding 3 common differences. So 2, 4, 6, 8. If I want here, it's like I added 2 3 times to get to the fourth term. So 2 plus 2 times 3, which is 6, is 8. Okay? So that we're adding the common difference 3 times to get to the fourth term. So that's where this formula comes from. Here's your first term, T1, for each one, plus n minus 1. So notice if I want the third term, we're adding 2 common differences. If I want the fourth term, that's 3 common differences away. That's why it's 1 less. And then d is your common difference times the common difference. Okay, so that's the formula. The 2 n's in the formula are always the same. So let's practice making it. For the arithmetic sequence, find the general term. What is it really saying when it says general term? Make that the formula, the equation. Okay, so we're going to plug it into our formula. What do we need to plug it into our formula? We need to know our common difference and our first term. Do we know that? Or can we figure that out? Yeah. Common difference. Want to do that first or first term? Sure, common difference. What are we adding each time? 4. So it is arithmetic. They didn't lie to us. That's good. Term 1, 8. Okay. So now we can actually make the formula. And it's the general term, meaning we're just leaving it as general. It's almost like a y equals and then an x. Instead of y, we use t of n. Instead of x, we're using n. Ooh, I can show you something on your calculator too. Okay. Anyways, t of n equals term 1 is 8 plus, so we're plugging it in to the formula up above, plus bracket. We're going to leave it as n minus 1 because we're making it general. We're not talking any specific term. We're going to leave it general. Times our common difference, which I'm going to put in brackets so we don't make a mistake with negatives, if it is negative, is 4. Okay? Now, if I ask for the general term or formula, theoretically you could leave it here and you're done. It's correct. It would work every time if you know your n value. However, math teachers like things simplified, right? So if I ask you to make the formula and simplify it, then you need to do what? Get rid of the brackets. And it's a little backwards because the monomial is at the back. We have to bring the 4 in. Yeah. So simplifying it is always nice. It looks prettier. Especially if they tell you to simplify. They didn't tell us to, but we're going to get in the habit of doing it. Because all your answers in the textbook, when you check your work, will be simplified. Okay, 8 plus, so 4 times n. Good old distributive law from Math 9 and 10. 4n minus 4. Good. I distribute the 4 into both. And then last, we collect like terms. Here they are. Those are our like terms. And just like mx plus b from 10c, we like the variable first and then the constant. I'm going to put the n first. So 4n, 8 minus 4, plus 4. So there it is. You can check your work one of 2 ways. First way is I could just plug in, like n is 1. 4 times 1 plus 4, does that give me my first term of 8? Yeah, and then I could try n2, the second term. 4 times 2, 8 plus 4 is at 12? Yup. Okay, so it works. By plugging in our different n values, so if I plugged in term 1, 4 times 1 plus 4 8. Yeah. Plug in term 2. 4 times 2 plus 4. Is that 12? Yep. Right? That's one way. Okay. So that's a way to check your work. Another way is with your calculator. You could use y equals. So y equals, and then I would write, instead of n for x, oops, 4x plus 4, and then go to my table. And my table should have the same sequence. So second graph, oh, let me make this bigger for you. Okay, so there's term 1 is 8, term 2, 12, term 3, 16. And then really quickly, if I wanted to say the sixth term, I could just see the sixth term is 28. Okay, so your table can help you too. Good times. I know, it seems long. We are just going to get to the end of this page, and that's it for today. So, finding term 20. Now is it easy to find term 20 now that you have a formula? Yep. Did you already figure it out? Some of you? You could probably do that one in your head, maybe. 80 plus 4, 84. Okay. If you used your calculator, you could have also, let's do that. Okay, you could have scrolled down to the 20th term, and there it is, 84. Okay. All right, what I'd like you to do is try number 3. So make the equation. Give it a shot, just like we did above. So preferably, we use distributive law and simplify this. 12 plus. Don't forget to multiply both of them by the common difference. Where you need to be careful is if your common difference is a negative, that affects the sign, right? So a side note, if I had, say, n minus 1 times negative 3, when if I bring in the negative 3, it becomes a minus 3n plus 3. Right? That sign, negative 3 times n, negative 3. Negative 3 times negative 1 plus 3. That's not this example. I'm just saying as a side note. Okay? Be careful if your common difference is negative. In this case, it's not, so we're okay. And you're less likely to make a mistake. 3n minus 3. Collecting like terms, you should have had 3n plus 9. Okay? And so that's what you should have had for your formula. And what was the 10th term? 3 times 10 plus 9 is 39. Good. We have one more example. Okay, it says, how many terms are there in the following sequence? Negative 3, 2, 7, and it goes all the way to 152. Infinite or finite? Fine, yeah, it has to be because they're asking us how many terms are there. And you could also see it ends at 152. Okay, important information. No matter what, we always need to know our first term and our common difference. It's a good starting spot. What's my first term? Negative 3. And what's my common difference? What are we adding each time? Plus 5. Okay. Now, if we look at this formula, term 1 plus n minus 1 times d. If you want, we could start by just plugging in term 1 and d. We could also plug in other information. What are they looking for? So everything here, there's 4 different variables. Term 1 we know, common difference we know. The other 2 variables are t of n and n. So when it asks how many terms, is how many terms t of n or n? N stands for the number of terms. Okay? So by definition, the number of terms is n. That's what we're looking for. That's our unknown. Do we know our t of n? Remember I told you, I briefly mentioned this. T of n is our last term. Yeah, so 152 is our last term. We want to know what is n when t of n is 152. Okay, so there's two ways to solve this problem. You could first just plug, like ignore this stuff and just make the formula, and then we could go from there. Or we can just plug all in what we know right now. So let's plug in everything we know. We know t of n is our last term of 152. Okay, first term we know, -3, plus, do we know n? No. n minus 1, common difference is 5. Can we solve for n now? Sure, just algebra. First step, just like before. Where do I want to begin? Yeah. That second step. Close. You probably already did it. Before we can combine like terms. Are you saying, well, you could, actually you could add the 3 to the other side right now. Yeah, you could do that. Yeah. I would personally get rid of the brackets, but you're welcome to add the 3 first. Okay? So either would work. I would get rid of the brackets, but that's just me. But if you want to add 3 to the other side first, you can do that too. So I'm going to get rid of those brackets. I don't like them. And then I have 5n. Collecting -3 minus 5 gives us -8. And so now we're just using grade 9 algebra, everyone's favorite thing ever, right? Add 8 to the other side. We want to get n by itself, right? That's our goal. So to get n by itself, we have to take care of the any addition subtraction first. 160 equals 5n. Now what? Divide by 5. And that gives you 32. 32. Okay, so term 32 is 152. That's what that means. The 32nd term is 152. So we have 32 terms. I use the 3 dots a lot. Have you seen these before? Dot, 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 like that? Means therefore in math? Yeah. Okay. It's like a bowling ball that's in a snowstorm and it's white. No. Or a therefore symbol. Therefore. I guess that's what I just said. That's what it means, therefore. Okay. All right, so what is your assignment? Your assignment is page 16 to 20, I think it is. Or just 6. I think it's just all on page 16. Numbers 1 to 5. Okay.